Hi, my name is Helen and I'm going to be talking about my final year project with Monash University's ECSE department. My FYP was an individual project on balancing shared bike systems supervised by Dr. Winita Griggs, and the final product is an app that can be used to book a bike within a simulated bike share system that is able to maintain its bike inventory levels. So I'm sure you've seen these kind of bike share systems around where you're able to borrow a bike and then return it to another station when you're done with it. And they're pretty popular in cities that have traffic congestion problems like New York and London. However, as you'd imagine, because there are a finite set of docks and bikes available at each station, there's going to be situations where a customer wants to borrow a bike but can't because that station is empty. Or probably more frustrating is if a customer wants to return a bike but can't because that station is full. Because people are taking these kind of one-way trips, we end up with a demand imbalance where some stations will be full and others will be completely empty. The focus of my FYP is on rebalancing this imbalance by intervening in the system. And currently there are two main ways that people have looked into achieving this. So the first is called operator-based methods, and here the focus is on meeting customer demand by employing trucks to manually relocate bikes and docks to where needed in the system, kind of on a rolling basis. But the problem with this method is it detracts from the green appeal of the shared bike system, and it also contributes to the traffic congestion problem that's trying to be solved in the first place. So this has kind of brought to surface another form of rebalancing called user-based methods, and here the focus lies more on redistributing demand for bikes rather than the supply of them. Here, the operator attempts to persuade customers into altering their arrival and departure stations, and this is what my project will focus on. As I mentioned earlier, the final product is the mobile application. But before designing that, I needed to find a control algorithm that could effectively rebalance the bike share system. Therefore, that splits my project up into two parts, the first being more research-based, while the second is more design and build-based. When researching, I found a paper that proved these systems could be rebalanced purely through user cooperation. And what they did was they encouraged users to shift their origin to the fullest bike station, or their destination to the emptiest bike station within some radius of their original target. However, they found that when this radius exceeded 700 meters, the overall satisfaction level of customers began to drop. This was because too many users would be assigned a station that initially had the most bikes within that neighborhood, but upon arrival, that station no longer had enough bikes to satisfy the demand of all the customers. This phenomenon was labelled flapping by another work within the field, and they addressed it by adding an element of randomness into the algorithm. It's a very simple concept where users are assigned a nearby station with a probability proportional to the number of available bikes at that station. So for example, if I want to go to station C, but station C is empty, and A and B are within walking distance, the operator would assign me to station A 75% of the time and B 25% of the time, instead of just sending me to A 100% of the time. And they call this a stochastic assignment process. However, in this piece of work, they only test their algorithm on a system with two stations, so that negative effect of increasing the neighborhood radius beyond a certain point isn't looked at. So I take this stochastic assignment algorithm and apply it to my own simulated bike share system that contains more stations. I use an open source mobility emulator called Sumo that can be used to host a network of roads and junctions that can then be used to simulate the bike share system on. This is then interfaced with Python to dynamically introduce users into the system. Here is a set of results from the test I ran. A quality of service metric is used to compare the different algorithms, where 100% means all customers were able to borrow or return a bike where they wanted to. For comparison, here is the bike system after 3 hours of simulation with no control method in place. On the left, we can see the inventory levels of all 10 stations over time, and clearly there's a huge imbalance. This has led to a low quality of service of 45%. Next, the stochastic algorithm is applied and there's a huge improvement with quality of service achieving 69%. However, the fluctuations in inventory are still quite large, with some stations hitting up to 200%. The stations with the larger fluctuations had more riders arriving or departing at those stations over some time period. And it's likely that we're seeing that flapping phenomena here. Recall that the stochastic algorithm used delayed occupancy information, as it does not account for the time taken for the user to arrive at the station that is assigned to them. To mitigate this, a really simple way of getting the future occupancy levels of stations is implemented, and I used the predicted occupancy in the stochastic assignment algorithm in place of the delayed information. We basically just project the occupancy of each station across some time horizon at the start of the simulation. And then each time a customer reserves a bike for some departure time, the predicted occupancy of that station from the reserved departure time to the end of the time period is decremented. It's a very simple and computationally cheap way of getting an estimate of occupancy levels. And looking at the figure here, it definitely improved our results. But what I noticed here was that stations 3 and 5 quickly fall to below 20% occupancy, while the others remain closer to full capacity throughout the 3 hours. While this did not cause any issues in this set of simulations, I thought having station fuel levels sit close to the boundaries would be risky if there was a sudden burst of demand or supply. Therefore, next we changed the target fuel level according to the average fuel level of the group of stations within walking distance. For example, consider this neighborhood where each bike station has 5 bikes available. According to the previous algorithm, a user would be assigned to any of these stations with an equal probability of 33%. However, unknown to the previous algorithm is that each of these stations have a different capacity. In other words, stations A and C are much closer to being at full capacity despite the absolute number of bikes being the same at each station. Therefore, we calculate the fuel level as a ratio of each station and then get the average. The capacity of each station is then multiplied against the average ratio and subtracted from the number of bikes available to get the number of extra bikes compared to the target fuel level. If this number is negative, we simply round it to 0. We then use the number of extra bikes to calculate the probability of a user being assigned to that station. With this modification in place, the user now has a 10.45% probability of being assigned to station A and an 89.55% probability of going to station C, while previously he was equally probable of going to any of the stations. This modification does improve results, and we achieve a quality of service of 100%. The quality of service rankings clearly show that the last algorithm is our winner. But what about that neighborhood radius I was talking about earlier? Well, I ran some tests varying this value, and as expected, with the base stochastic assignment algorithm, quality of service increases with the radius as there are more alternative stations to distribute demand and supply to. That is until we hit 700 meters, where the radius becomes too large and flapping starts to occur. However, the simulations with the estimated occupancy levels does not exhibit this drop-off, with the algorithm that varied the target fill rate performing best across almost all tests. But it's unrealistic to expect all riders are willing to walk the same distance. Therefore, we vary this value on a user-by-user level, and it's promising to see that the altered control algorithm outperforms the other methods. And this more or less concludes the first half of the project, where basically a whole bunch of simulations was run to find an algorithm that would best rebalance this bike share system. And of the simulations run, it seemed that overall the stochastic algorithm that used the predicted occupancy levels and varied the target fill rate according to the mean of the stations within the neighborhood performed the best. So that is what we adopt into the next part of the project. The next part of the project involved taking the simulated bike share system with the rebalancing strategy incorporated in it and allowing someone from the outside world to interact with it. To do that, I made a native Android app written in Java that lets you virtually book and borrow a bike from the simulated system. It communicates with the simulated system via a server written on Python through sockets using TCP/IP. Here, the remaining customers within the system are automated, and the app simply allows us to take control of a single rider. I can walk you through the functionalities of the app and how it works. Upon launching the app, you get a login page where you can log in or create an account if you don't have one. Because I already have an account, I'm just going to log in, and it'll send this info to the server where it confirms that the user and password entered matches the ones in the user database. now that I have logged in, I can start my reservation for a bike. First, you would enter where you want to depart from, and you can filter by name, or you can open up the map view to see the stations visually. After selecting the station, you can enter where you want to depart. And finally, how far you're willing to walk, if at all. Submitting this sends this request to the server, which then processes this information and returns a list of stations that you can depart from within walkable distance. It will also return the recommended station according to the stochastic assignment algorithm. This will also show the estimated number of bikes at each station at the departure time, and assuming I'm a rule follower and I listen to the system, I'm just going to confirm my reservation at the recommended departing station. Once I have reserved a bike, the app displays this page where I can get some info about the reservation, and I can also get the directions or cancel the reservation. I can also pull up the QR scanner here, which is used to scan a loaded dock at the departing station. If I scan a QR code belonging to a different station from the one I reserved, I get this error message. But if I scan a QR code belonging to the station that I reserved, the bike is unlocked within that simulated system. And once I've actually borrowed the bike, the app is now periodically querying the server to check if I have docked the bike in the background thread. But ideally, I should now let the system know when and where I'm going to return the bike to. This is to help with the future assignment of bikes and docks for other users. I am asked where I want to return the bike and if I'm traveling directly there. This is so that the system can use the estimated travel time between the stations if I say I'm traveling directly there. But if I say I'm not, then I can input how long I want to borrow the bike for. And once again, I'm asked if I'm willing to walk for another station and how far, if so. Submitting this query to the server returns another list of stations that I can arrive at, as well as the recommended station according to the assignment algorithm. And once again, I can just confirm my reservation here. Once this is done, I can go back and alter my dock reservation. Otherwise, the app will remain at this state until the server says the bike has been returned, which concludes the booking process. Other functionalities of this app include the station search page. Here, you can view all the stations in the system in a list format, where everything can be sorted by distance, occupancy, or name. You can also favorite stations and sort it according to that. Clicking the Show More icon will bring up additional information, and pressing the map icon switches the view to the map view. Here, all the stations are shown as markers. And the colour of the marker depends on the station's fill level, where green indicates a fuller station and red indicates an emptier station. Pressing the refresh button will retrieve the current fill levels of the station and update it on the app. But you can also just pull down on any of the other pages to do this. Here is the profile page. You can see your little virtual card with username and name, and pressing the edit button in the corner allows you to change your profile details. This page also displays all your past trips that you've made, including the ID of the bike you borrowed. You can also choose to log out here, but if you don't log out, then you remain logged in when you close the app, and it's saved in the device's preferences, so you will automatically log in via the login page when the app is next launched. Logging out will force you to re-enter your details to get back in. And the app also remembers where you're up to in terms of the booking state, even if you close the app and reopen it. If I could redo this project, I would probably want to focus on the occupancy prediction algorithm, since there's a lot of research done in the area and the current algorithm is really simple. I think I got a little bit carried away with trying to make the app look pretty, and in terms of future work, it would be beneficial to test the algorithm on empirical data, since most of the testing data is currently generated using commonly made assumptions in the literature. And I would also want to look at how the modifications made to the base stochastic assignment algorithm affect its stability. But that about concludes this video. I hope it was enjoyable and thank you for watching.